Good afternoon, class. Mr. Pettibone here. Um, Day, who knows, of quarantine. It's been, what, month and a half now. Um, Unfortunately, Bug is still not feeling very well, so I kind of put him, Bug's right here, and that's his back, and he's just kind of. I built a fort around him so he can just relax and be warm and quiet. Um, hey, Spicy Pepper. Hey, Jackson. Um, so today is our last day for reviewing paper 2 type questions. And then next week we'll do paper 3, which has a different format from uh, paper 1 and paper 2. So, yeah, and the other thing is feel free to fill out the homework at your earliest convenience. And also your turning in the paper 1 work from last week this week as your quiz. Okay, so please send that to me with the proper title for the email. So that would be SL underscore. I've got the May 2018 time zone 2 and May 2018 time zone 2, and I'm going to be doing questions 4 and 5. You guys are going to be doing questions 3 and 6. So, question 4. Let me focus this and see if it looks better. Focusing? Okay. All right. Question 4. Looks like a circuit. The diagram shows a potential divider circuit used to measure the EMF of cell X. Both cells have negligible internal resistance. Okay. And so first of all, it says, state what is meant by the EMF of a cell. So EMF stands for electromotive force. And basically it is the potential difference produced by a battery when it outputs zero current. Okay? So what we learned about real batteries is that real batteries, the voltage droops the more current you're asking from the battery. So the electromotive force is it's sort of like the maximum voltage that a battery can produce. Okay. It says AB is a wire of uniform cross section and length 1 meter. The resistance of wire AB is 80 ohms. When the length of AC is 0.35 meters, the current in cell X is 0. Okay. So show that the resistance of wire AC is 28 ohms. Well, by the way, one thing I wanted to talk about is that the point value is somewhat, the point value of a problem is somewhat indicative of the difficulty of the problem. So if you get a problem and the point value is 1, it's a really simple answer. If it's 2, it's probably just a really simple calculation. If you see a problem that has a point value of 3 or 4, that's when you're really going to have to do work. So we know that the resistance is rho L over A, okay? And we know, so that would be the length of AC, all right? Now, what if I multiply and divide by the length of AB? So I have rho L over A times the length of AB over the length of AB. Okay. Then I'm going to rearrange this again. So I'm just going to flip these two guys' positions. Try and move this a little closer. Dang it, why did I mess with that? Feel like it's a little bit too far away. So I'm going to switch those, and I'll get rho times LAB over A times LAC over LAB. Now, if I look at this thing in parentheses, that's the resistance of the entire wire A to B, which I'm told is 80 ohms. Okay, so this is 80 ohms, and LC over LAC over LAB is well, the length of the wire is 1 meter. Okay, and okay. And the length of AC is 0.35. So this is 1 and this is 0.35. So we get 80 times 0.35, which is 28 ohms. Okay. So now we want to determine E. So E is the EMF of cell X. So let's see what this says here. It says when the length of AC is 0.35 meters, the current in cell X is 0. So what would make the current in cell X 0? Well, let me draw out the circuit here. So we have 12 volts. We got here's the length AC, and this is, as we said, it's 28 ohms. Okay, and the resistance of the entire wire, okay, is going to be 80 ohms, so the remaining resistance is 52 ohms. And then we have cell X right here, and this is 12 volts. Okay. So we have basically three currents in this circuit. Okay. We've got the current that's flowing out of this battery, and we've got the current that's flowing out of this battery. So I'll call that I1, and I'll call that I2. Okay. And both of those combine to go through the 28 ohm resistor. Okay. But we're told that the current in cell X is 0. So that means that I2 is, that means that this current is equal to 0. So normally what we would have is the current that goes through the 28 ohm resistor would be I1 plus I2. But because I2 is 0, the current that goes through the 28 ohm resistor is just I1. Okay? And then since this current is 0, that's the same current here. So we just have this current I1 going all the way around here. Okay? So we can figure out what I1 is just by using Ohm's law. It'd just be V over R. So it would be 12 over 80, which would be 0.15 amps. Then I could calculate the voltage across the 28 ohm resistor, which would be I1 times 28, so it would be 0.15 times 28. And that gives 4.2 volts. Now, this resistor is in parallel with the battery, so that must also be the voltage of the battery. So that means that the voltage of the battery is 4.2. Okay, so that was question 4. And now I'm doing question 5. Let me see if I have any questions. No questions. All right, looks like this is a climate change problem. Energy production, climate change. Wow, that's really not drawn to scale. 34 meters and 110 meters are the same distance. Water leaving the upper lake descends a vertical distance of 110 meters and turns the turbine of a generator before exiting into the lower lake. Water flows out of the upper lake at a rate of 1.2 times 10 to the 5th cubic meters per minute. The density of water is 10 to the 3rd kilograms per cubic meter. Estimate the specific energy of this water storage system, giving an appropriate unit for your answer. Okay, so specific energy is energy per kilograms, energy per mass, okay? So if we think about what kind of energy does the water have? It has gravitational potential energy, so it has mgy. All right. And then if we look at how much mass does it have, it just has m. So we see the masses cancel out. Okay? The masses cancel out. So really the specific energy is just G times Y, where Y is sort of the average height of the water. Okay? So if we look at the average height of the water, it would be the middle of the upper lake. That's going to be the average elevation of the water that gets down to the turbine. So So I'm going to say the average height of the lake is 34/2, which would be, 17, which we then have to add to the 110. So the average height is about 127 meters. So I would say, and then we multiply that by 10, and we get 1,270 joules per kilogram of water. Okay? Part 2, it says show that the average rate at which gravitational potential energy of the water decreases is 2.5 gigawatts. All right. So we're trying to get power, right? Because it's watts. Power is energy per time. Okay? Energy per time is the same thing as energy per mass times mass per time. Okay? And then energy per mass times mass per time is the same thing as energy per mass times mass per volume times volume per time. So see how the m's cancel out and the v's cancel out, and I just get energy per time. So the energy per mass, I just calculated it, is 1270 joules per kilogram. The mass per volume, that's the density of the fluid, which I know is 1,000. And then the volume per time, that is this. This is cubic meters per minute. So I'm going to get 1.2 times 10 to the 5th cubic meters per minute. So I have to divide by 60 to get per second, right? Okay, and then I multiply all those together. 1270 times 10 to the 3rd times 1.2 times 10 to the 5th divided by 60, and I get 2.5 times 10 to the 9th watts. And 10 to the 9th is a giga, so it stands for a billion. So this is 2.5 gigawatts. All right, I. The energy storage system produces 1.8 gigawatts of electrical power. So the power, the useful power that goes out divided by the power that's produced is equal to the efficiency. So the power that goes out and is actually used by the world is 1.8, but sort of the amount that is released is 2.5 gigawatts. So the ratio of those two is going to give us the efficiency. Again, we can see this is a one-point problem, so it should be a very simple calculation. So the efficiency, 0.72, which is the same thing as 72%. 72% efficient. Okay, we've got one more part. After the upper lake is emptied, it must be refilled with water from the lower lake, and this requires energy. Suggest how the operators of this storage system can still make a profit. Wow, that's a weird question. I'm trying to figure out what this has to do with physics. I don't know. Your guess is as good as mine. Sometimes the IB exam is going to ask you a question and you just have to kind of like think on your toes and come up with an answer. I'm thinking about for most dams, um, you know, for most dams, energy is, or the dam is replenished just by natural means, right? It's like on a river or something like that, and the water drains into the. Um, so that's one thing. Another thing is how much are we selling the energy for, right? So maybe for every, that's what I'm going to go with. I'm going to go with this. I'm going to say you sell the power at a rate that allows the operators to have extra money to pump the water back up. I don't know. So basically sell it for double what it costs to produce it so that you can pump it back up. That's my guess. Um, yeah. So I'm curious. I'm just going to read later on I'll just read what they said. You know what? Maybe I'll read what they said right now. Actually, my internet is too slow while I'm streaming. So at any rate, thank you for watching. That's my lesson for today. And I'll see you next week. I hope you guys have a really nice weekend. Next week we'll be doing paper 3. So miss you guys. Bug is still here. I hope he feels better soon. He stayed in his cave for the entire lesson. Okay, bye guys.